The National Electrical Code, or NEC, dictates the requirements for grounding electrode systems. According to the NEC, specifically Section 250.52a and 2, the metal building frame or the cold water pipe are considered the main grounding electrodes. However, it is crucial to understand the supplementary requirements outlined in NEC Section 250.53d2. This section specifies that when a cold water pipe is used as the main grounding electrode, it must be supplemented by an additional grounding electrode such as a grounding rod, a grounding ring, or another type of approved grounding electrode. The purpose of the supplementary electrode is to enhance the overall effectiveness and reliability of the grounding system. To summarize, the metal building frame or the cold water pipe can serve as the main grounding electrode. But the code requires that if a cold water pipe is used as the primary grounding electrode, it must be supplemented by another approved grounding electrode like a rod. The size of the grounding electrode conductor is determined by NEC Table 250.66. For example, if the ungrounded service entrance conductor is 1100 kcmil copper, then the grounding electrode conductor to the ground rod or other electrodes must be no smaller than #2 AWG copper. It is essential to consult this table to ensure the correct conductor size based on the specific parameters of the electrical service. In a typical scenario where you are grounding to both a ground rod and a cold water pipe, you would use #6 AWG copper wire to connect to the grounding rods and #4 bare copper wire to connect to the main cold water pipe. Always adhere to the NEC guidelines and the local electrical codes to ensure the safety and compliance of your grounding system. The effectiveness of a grounding system is heavily dependent on the conductivity of the soil. High soil resistivity hinders the ability of the grounding electrode to dissipate fault current effectively. Soil resistivity is measured in ohms meter or ohms centimeter and varies depending on factors like moisture content, temperature, and chemical composition. Methods to reduce soil resistivity include driving ground rods deeper, using multiple ground rods, or treating the soil with ground-enhancing compounds. The National Electrical Code, or NEC, provides specific guidelines for the installation and maintenance of grounding electrode systems to ensure electrical safety and proper system function. Section 250 of the NEC covers grounding and bonding requirements, specifying the types of electrodes that can be used, their installation methods, and the minimum sizes of grounding conductors. The main grounding electrode, as defined by the NEC, is typically the metal frame of a building or a metallic water pipe that is in direct contact with the earth for at least 10 feet. In many cases, a supplemental grounding electrode, such as a ground rod or ground ring, is required to enhance the effectiveness of the grounding system. When using a metallic water pipe as the main grounding electrode, it is essential to ensure that the pipe is electrically continuous and that any insulating sections are properly bonded to maintain continuity. Additionally, a supplemental grounding electrode must be installed to provide an alternative path for fault current in case the water pipe becomes compromised. Ground rods, typically made of copper or galvanized steel, must be at least 8 feet long and driven into the ground so that at least 8 feet of the rod is in contact with the soil. The spacing between ground rods should be at least equal to the length of the rod to ensure that they do not interfere with each other's grounding capabilities. The grounding electrode conductor, which connects the grounding electrode to the service equipment, must be sized according to NEC Table 250.66 based on the size of the service entrance conductors. This conductor must be securely connected to the grounding electrode using approved methods, such as exothermic welding or listed connectors. Proper bonding of metallic components, such as electrical enclosures, conduit, and equipment frames, is crucial to minimize the risk of electrical shock and ensure that fault current can safely return to the source. Bonding jumpers must be sized according to NEC Table 250.102 and installed to provide a low impedance path for fault current. Regular inspection and maintenance of the grounding system are necessary to ensure its continued effectiveness. Grounding connections should be checked for corrosion and tightness, and ground resistance measurement should be taken to verify that the system is performing within acceptable limits. Any deficiencies, such as loose connections or high ground resistance, should be promptly addressed to maintain the integrity of the grounding system. In summary, a well-designed and properly installed grounding system is essential for electrical safety and the reliable operation of electrical equipment. Adherence to the NEC guidelines and regular maintenance are critical to ensure that the grounding system functions effectively in protecting people and property from electrical hazards. Grounding electrode systems are integral to electrical safety. The grounding electrode system provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. This rapid clearing of faults minimizes the risk of electrical shock and equipment damage. A properly designed grounding electrode system also helps to stabilize voltage during normal operation, reducing voltage fluctuations and improving the performance of sensitive electronic equipment. Effective grounding is crucial in mitigating the effects of lightning strikes. The grounding system provides a path for lightning current to safely dissipate into the earth, preventing damage to electrical equipment and reducing the risk of fire. Grounding electrode systems are governed by stringent standards and regulations to ensure their effectiveness and reliability. The National Electrical Code, or NEC, Article 250 provides comprehensive requirements for grounding and bonding, specifying the types of grounding electrodes, their installation methods, and the minimum sizes of grounding conductors. Local electrical codes and regulations may also impose additional requirements or restrictions on grounding electrode systems. Common types of grounding electrodes include ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, often referred to as UFRs. Ground rods are typically made of copper or galvanized steel and are driven into the earth to provide a direct connection to ground. Ground plates are flat metal plates buried in the earth to provide a larger surface area for grounding. Metal underground water pipes can serve as effective grounding electrodes if they are in direct contact with the earth for at least 10 feet and are electrically continuous. Concrete encased electrodes, or UFRs, consist of a steel reinforcing bar embedded in concrete foundations or footings, providing a reliable and long-lasting grounding connection. The selection of the appropriate type of grounding electrode depends on factors such as soil conditions, local regulations, and the specific requirements of the electrical system. Soil resistivity is a critical factor in determining the effectiveness of a grounding electrode system. High soil resistivity increases the impedance of the grounding path, reducing its ability to dissipate fault current. Soil resistivity varies depending on factors such as moisture content, temperature, and chemical composition. Methods to reduce soil resistivity include driving ground rods deeper, using multiple ground rods spaced apart, or treating the soil with ground-enhancing compounds. Proper installation and maintenance of grounding electrode systems are essential to ensure their continued effectiveness. Grounding connections should be inspected regularly for corrosion and tightness, and ground resistance measurements should be taken to verify that the system is performing within acceptable limits. Any deficiencies, such as loose connections or high ground resistance, should be promptly addressed to maintain the integrity of the grounding system. In summary, grounding electrode systems play a vital role in electrical safety and equipment protection. By providing a low impedance path for fault current, stabilizing voltage, and mitigating the effects of lightning strikes, grounding electrode systems help to ensure the safe and reliable operation of electrical systems. Adherence to established standards and regulations, proper installation and maintenance, and consideration of soil conditions are essential for achieving effective grounding. Electrical grounding ensures safety by providing a low resistance path for electrical currents to flow back to the source in the event of a fault, such as a short circuit. This low resistance path allows the current to quickly trip a circuit breaker or blow a fuse, cutting off the power and preventing electrical shock or fire hazards. Without proper grounding, fault currents could flow through unintended paths, such as a person touching a faulty appliance, leading to severe injury or death. Grounding also helps to stabilize voltage levels in an electrical system, reducing voltage fluctuations and preventing damage to sensitive electronic equipment. In addition to safety, electrical grounding is also important for protecting electronic equipment from damage due to power surges and lightning strikes. A properly grounded system provides a path for these surges to safely dissipate into the earth, preventing them from damaging sensitive components. The National Electrical Code, or NEC, provides detailed requirements for electrical grounding to ensure safety and proper system operation. These requirements cover everything from the types of grounding electrodes that can be used to the size and installation of grounding conductors. Grounding electrodes are typically metal rods, pipes, or plates that are buried in the earth to provide a connection to ground. The NEC specifies the minimum size and depth for grounding electrodes, as well as the requirements for their installation. Grounding conductors are used to connect electrical equipment and systems to the grounding electrode. The NEC specifies the minimum size for grounding conductors based on the size of the circuit they are serving. The NEC also requires that grounding conductors be properly identified and protected from damage. In addition to the NEC, local electrical codes may also have specific requirements for electrical grounding. It is important to consult with a qualified electrician to ensure that your electrical system is properly grounded and meets all applicable codes and regulations. Regular inspections and maintenance are also essential to ensure that the grounding system remains effective over time. Grounding connections should be checked for corrosion and tightness, and ground resistance measurement should be taken to verify that the system is performing within acceptable limits. Any deficiencies, such as loose connections or high ground resistance, should be promptly addressed to maintain the integrity of the grounding system. Effective grounding is crucial in minimizing the risk of electrical shock, preventing damage to equipment, and ensuring the safe and reliable operation of electrical systems. Adherence to established standards and regulations, proper installation and maintenance, and regular inspections are all essential for achieving effective grounding. Understanding the principles and practices of electrical grounding is essential for anyone working with electrical systems, from homeowners to electricians. This knowledge can help to ensure the safety of people and property and prevent electrical hazards. Grounding electrode systems are a critical component of electrical safety, serving as the primary means of protecting people and equipment from electrical shock and damage. These systems provide a low impedance path for fault currents to return to the source, allowing overcurrent protection devices, such as circuit breakers and fuses, to quickly clear the fault and prevent hazardous conditions. The grounding electrode system consists of one or more grounding electrodes, which are conductive objects that establish a direct connection to the earth. Common types of grounding electrodes include ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, often referred to as UFRs. Ground rods are typically made of copper or galvanized steel and are driven into the earth to a depth of at least 8 feet. Ground plates are flat metal plates buried in the earth to provide a larger surface area for grounding. Metal underground water pipes can serve as effective grounding electrodes if they are in direct contact with the earth for at least 10 feet and are electrically continuous. Concrete encased electrodes, or UFRs, consist of a steel reinforcing bar embedded in concrete foundations or footings, providing a reliable and long-lasting grounding connection. The grounding electrode conductor connects the grounding electrode to the electrical system's grounding bus bar, which is typically located in the main service panel. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The grounding electrode system must also be bonded to other metallic components in the building, such as metal water pipes, gas pipes, and metal building frames, to create a common ground reference and prevent voltage differences between these components. Bonding is accomplished by connecting these metallic components to the grounding busbar using bonding jumpers, which are typically copper conductors sized according to NEC Table 250.102. Proper installation and maintenance of the grounding electrode system are essential to ensure its effectiveness. Grounding connections should be inspected regularly for corrosion and tightness, and ground resistance measurements should be taken to verify that the system is performing within acceptable limits. Any deficiencies, such as loose connections or high ground resistance, should be promptly addressed to maintain the integrity of the grounding system. In summary, grounding electrode systems are a vital component of electrical safety, providing a low-impedance path for fault currents to return to the source and protecting people and equipment from electrical shock and damage. Proper design, installation, and maintenance of the grounding electrode system are essential to ensure its effectiveness. The main grounding electrode is key for electrical safety. The National Electrical Code, or NEC, establishes minimum requirements for grounding electrode systems, but local codes may have additional requirements. Understanding the specific requirements applicable to your location is essential for ensuring compliance. The NEC requires that all grounding electrodes be electrically connected to form a grounding electrode system. This connection is typically achieved using a grounding electrode conductor, which must be sized appropriately for the service entrance conductors. The grounding electrode conductor must be securely connected to the grounding electrodes using approved methods such as exothermic welding or listed connectors. Grounding electrode systems should be designed to minimize ground impedance. Low ground impedance ensures that fault currents can quickly and easily return to the source, facilitating the operation of overcurrent protection devices. Ground impedance can be reduced by using multiple grounding electrodes, spacing them apart, and treating the soil with ground-enhancing compounds. Regular inspection and testing of grounding electrode systems are essential to ensure their continued effectiveness. Ground connections should be checked for corrosion and tightness, and ground resistance measurements should be taken to verify that the system is performing within acceptable limits. Any deficiencies, such as loose connections or high ground resistance, should be promptly addressed to maintain the integrity of the grounding system. Grounding electrode systems play a crucial role in protecting sensitive electronic equipment from damage due to power surges and lightning strikes. A properly designed grounding system provides a path for these surges to safely dissipate into the earth, preventing them from damaging sensitive components. In addition to providing a path for fault currents, grounding electrode systems also help to stabilize voltage levels in an electrical system. This voltage stabilization can improve the performance of sensitive electronic equipment and prevent damage due to voltage fluctuations. Grounding electrode systems are a critical component of electrical safety, and their proper design, installation, and maintenance are essential for protecting people and equipment from electrical hazards. Adherence to established standards and regulations, regular inspections and testing, and attention to detail are all necessary for achieving effective grounding. The effectiveness of the grounding system hinges on the type of soil present at the location. Soil resistivity is a measure of how well a soil conducts electricity. Soils with low resistivity are better conductors and provide a more effective path to ground. Factors affecting soil resistivity include moisture content, temperature, and the presence of dissolved salts and minerals. Sandy soils typically have high resistivity, while clay soils have lower resistivity. The NEC recognizes several types of grounding electrodes, including metal underground water pipes, metal frames of buildings, concrete encased electrodes, ground rings, and ground rods. Metal underground water pipes must be in direct contact with the earth for at least 10 feet to qualify as a grounding electrode. The metal frame of a building can be used as a grounding electrode if it is effectively grounded. Concrete encased electrodes, also known as UFERs, consist of a steel reinforcing bar encased in concrete. Ground rings are made of bare copper wire and are buried in the earth in a circular configuration. Ground rods are driven into the earth and are typically made of copper or galvanized steel. The size of the grounding electrode conductor is determined by NEC Table 250.66 and depends on the size of the service entrance conductors. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods such as exothermic welding or listed connectors. When multiple grounding electrodes are used, they must be bonded together to form a grounding electrode system. The bonding jumpers used to connect the grounding electrodes must be sized according to NEC Table 250.102. Grounding electrode systems should be inspected regularly for corrosion and damage. Corroded or damaged grounding electrodes should be replaced to ensure the effectiveness of the grounding system. Ground resistance testing is used to measure the resistance of the grounding electrode system to earth. The measured resistance should be below a certain threshold to ensure that the grounding system is functioning properly. Ground resistance testing should be performed by a qualified electrician using calibrated test equipment. Grounding electrode systems are an essential part of any electrical installation and should be properly designed, installed, and maintained to ensure the safety of people and property. In addition to complying with the NEC, it is important to follow local codes and regulations related to grounding electrode systems. Local codes may have additional requirements that must be met. Always consult with a qualified electrician to ensure that your grounding electrode system meets all applicable requirements. Effective grounding is a critical aspect of electrical safety and should not be overlooked.